Bueller, Bueller, Bueller.
Trig equations. Now, trig equations, when solving them, you can either be solving them on an interval, either in degrees or radians, or you could be solving for the general solution. So we're going to go through both examples in this video. So if I have an equation like this, 4 cosine theta plus 2 equals 0, and I'm solving for theta on an interval of degrees between 0 and 360, there's a couple things I need to find. First off, I need the reference angle, and secondly, I need the quadrant, and that will help me determine what the actual values of theta are. So let's solve this equation to figure out what cosine itself is equal to. So I'm going to isolate cosine like I would in any other equation. So by first subtracting by 2, so I get 4 cosine theta is equal to negative 2. Divide both sides by 4, and I get cosine of theta is negative 2 over 4, which is just negative 1/2. Now, there's a couple things that help me determine what quadrant I'm in and what my reference angle is. First, you can remember for the shortcut, a smart trig class helps me determine when these trig values are positive and negative. So cosine will be positive in quadrant 4 and quadrant 1, which means it's negative in quadrant 2 and quadrant 3. So I'll either be in quadrant 2 or quadrant 3. And again, that is being determined by the sign. Since it's a negative value, cosine is negative in these two quadrants, so I know I'm in quadrant 2 or quadrant 3. The other portion is the value 1/2 is the ratio for cosine, and one of those basic reference angles that gives me that ratio is 60 degrees. So I know that my reference angle will be 60 degrees. So the two, in order to get this information, it's the ratio and the sign. Now, if it's 60 degrees in quadrant 2 and 3, you could do a quick sketch to see what those angles would look like. So here's 60 degrees in quadrant 2, and there's my reference angle. It's always made with the x-axis. And here's 60 degrees in quadrant 3, again made with the x-axis. The actual angles is always measured from the positive x-axis, which is here, up to this terminal side. So if this is 180 degrees and I've come back 60 degrees from it, that leaves me with 120 degrees in my actual angle. And if this is, again, 180 and this is 60 more than that, then my actual angle, which comes all the way around and goes to this, will go 180 and then another 60, or 240 degrees. Okay, so my actual angle measures between the values 0 and 360 are 120 degrees and 240 degrees. So those are my solutions. The other type of interval you might see is a radian interval, so from 0 to 2 pi. So we're going to do these two equations in radians, and these are slightly more difficult because they require factoring. So you have to solve them like another type of equation and then figure out the angle measures. So let's get started. Notice that this is a sine squared and a sine, which makes this a quadratic equation. So it's going to factor like any other quadratic equation. I'll have a factor of sine of x in each of these in order to get a sine x squared factor. And then I'm looking for numbers which multiply to negative 4 and add or sum up to 3. And that'll be negative 3. That'll be positive 4 and negative 1. So sine x plus 4, sine x minus 1. Those numbers will multiply to negative 4 and add to negative 3. Then by the zero product property, that tells me that either sine of x is equal to negative 4 or sine of x is equal to 1. Unfortunately, negative 4 is outside of the range of sine, so that was going to get rejected. And left with sine x equals 1. Now, there's a couple ways you can do this. You can think of the unit circle. Since sine x equals 1 is one of those special ones, it's not one of those reference angle ones. You can think of the unit circle, and sine is the y values, and it will equal 1 on the unit circle here, which is at pi over 2. Or you can think of the graph of sine. So the graph of the sine function looks like this. It finishes its period in 2 pi, which means this is halfway through its period, which would be pi, and it equals 1. It goes between 1 and negative 1 here, which is halfway between 0 and pi, which is at pi over 2. However way you slice it, you'll get x is pi over 2. Now the reason I did not use a reference angle for this example is that those special values, for sine it's positive 1, negative 1, and 0. For cosine it's positive 1, negative 1, and 0. Those special values are quadrant angles, and those will not have reference angles. Okay, so let's look at the next one. I'm going to draw a line so I don't get any cross. There we go. Okay, so here we go. Okay. Now this one common mistake that people want to make, I'm going to do it in red so that you can see, is that they'll go right here and say, oh, I can just divide by sine x. No, you can't, because sine x could be 0. So you're not able to divide both sides by sine x. So do not do that. You can never divide by something that is a variable because you cannot account for the fact that it could be 0. So here's the appropriate way to solve. What I'm going to do instead is subtract the square root of 3 sine x to the other side and solve by factoring just like we did over here. So this will be minus the square root of 3 sine x equals 0. Now notice, the first thing you should check for when you're factoring is a greatest common factor, which in this case is sine. So I'm going to factor out that common factor of sine of x, and I'm going to be left with tan of x minus the square root of 3 is equal to 0. So that either means that sine of x is equal to 0, or tan of x is equal to the square root of 3. Well, again, 0 is another one of these special values. In fact, I left it over here. If I go back, sine of x will equal 0, here at 0, here at pi, and then again at 2 pi. But since I'm only looking for values less than 2 pi, the only two answers I'll be including from this are x being 0 and pi. So I get those off of my sine graph. You could also, again, unit circle when sine is 0, it's 0 here and here. So those two values, 0 and pi, is what I'm including. Tan x is the square root of 3. That happens, that is not a quadrant angle situation, so I'm going to need my reference angle in quadrants. So my reference angle, when it's the square root of 3, is 60 degrees, which in radians is pi over 3. And then my quadrants, tangent is positive. Again, you can do this. A smart trig class. Tangent is positive in quadrant 3 and quadrant 1. So pi over 3 in quadrant 1 is conveniently pi over 3. And if you want to do a sketch of pi over 3 in quadrant 3, here's pi over 3. I'll do an arrow. Here's pi over 3. It's my reference angle. This is 0, pi over 2, and pi. So the actual angle I'm looking for is pi plus pi over 3, which is 1 1/3 pi, or 4 pi over 3. Okay. So those are my two solutions from that portion, and what I end up with altogether are 4 answers. So x could be 0, could be pi over 3, could be pi, or could be 4 pi over 3. So I get 4 solutions, 2 from sine and 2 from tangent. Now, one other thing, if there's no interval given and it's asked for the general solution, it's really asking for each quadrant angle, or each angle, the angle that falls in each quadrant, and then all of their coterminal angles. So we'll figure out how to represent that as we go through this question. So secant squared of x minus 2 equals 0. So then if I do this, I get secant squared of x equals 2, which tells me that secant of x, when I square root both sides, so when I take square roots, I'm taking square roots of both sides, and whenever I take square roots, I need a plus or a minus, account for those two solutions. This will be plus or minus the square root of 2. We'll recall that secant is just the reciprocal of cosine. So this is cosine of x is equal to plus or minus 1 over the square root of 2. Okay, so I've taken the reciprocal of this, which is just plus or minus the square root of 2 over 2. Okay, now I didn't specify degrees or radians, so I'm going to do both. So I'm going to do them side by side so that you can see how to do it in both situations. If it doesn't specify, you could pick either one. And so if you wanted to do it in degrees, you could do it in degrees. If you want to do it in radians, you could do it in radians. But whichever you do, I'm going to need my reference angle, which for rad 2 over 2 is 45 degrees, or pi over 4 radians. And I'm going to need my quadrants. Now, notice that cosine is positive or negative. Well, that really accounts for all 4 quadrants. It's positive in 1 and 2, and it's negative in 3 and 4. So I have to do all 4 quadrants, 1, 2, 3, and 4. Okay, so 45 degrees in quadrant 1 is just 45. 45 degrees in quadrant 2 is 180 minus 45, should be 135. And quadrant 3 is 180 plus 45, which is, 225. And 180 in quadrant 4 would be 360 minus 45, which is 315. Okay? Now, here's how we account for the general solution, or all solutions. Any angle coterminal to this will also be a solution. So I'm going to add or subtract any full revolution. So what that means is this. I'm going to sketch 45 degrees here. Here's 45 degrees. Okay? Well, an angle which is coterminal to this would be one that comes all the way back around to here. So that's if I added one full revolution, which is 360 degrees when we're talking about degrees. So I can add 360 times any multiple, and I could do that to any of these. 360 times any multiple, 360 times any multiple, 360 times any multiple. For the radians, it's the same thing. I have my 4 quadrants, so I'm actually just going to write them down. I know what my 4 quadrants are. Okay, so pi over 4 in quadrant 1 would be pi over 4. Pi over 4 in quadrant 2 would be 3 pi over 4. It's pi minus a quarter would give me 3/4 of pi. Pi plus a quarter would give me 5/4 of pi in quadrant 3. And in quadrant 4, 2 minus a quarter would give me 1 3/4, which is basically 7 pi over 4. Okay, so now I'm going to again add or subtract any full revolution, but a full revolution in radians is 2 pi. So it's 2 pi times some number, plus or minus 2 pi times some number, plus or minus 2 pi times some number, and plus or minus 2 pi times some number. So this in green is my solutions in radians. Over here is my solutions in degrees. You do not have to do both of these every time, but whenever you see general solution, you must either give me the general solution in degrees or the general solution in radians.
You're still here? It's over. Go home. Go.